Hello, welcome to this video. I'm going to be talking about ARIMA, which is the autoregressive integrated moving average model. Here's an overview. I'm going to be giving the introduction to the model, answering the question, what is a stationary series? I'm going to be talking about the AR component, the MA component, and why we difference a series. Fourth, ACF, PACF, and then using AIC to optimize the model. And then fifth, I'm going to be putting it all together. So autoregressive integrated moving average model is a classical time series model for analyzing and forecasting time series. The model consists of the following: an autoregressive part, which past values influence the present, integrated, differencing to make it stationary, moving average, past forecasting errors influence the present, and then finally, it's flexible, can handle trends, shocks, and short-term dependencies. So here's some applications. It could predict stock prices and returns, sales forecasting in food, retail, and e-commerce. E-commerce, economic indicators, inflation, unemployment, and GDP, energy demand forecasting, and then healthcare, patient inflow, disease spread modeling, etc. What is a stationary series? Stationary data means that statistical properties, mean, variance, correlations, don't change over time. Constant autocorrelation structure, relationships between lags don't change. And then many time series models like AR and MA assume stationarity so that they can learn consistent patterns. If a series has a trend, keeps increasing, or seasonality repeats in cycles, predictions made on earlier data won't apply later. So there needs to be some kind of consistency in the data, and we need to difference data. So what is differencing? We see a linear trend differencing here of like YT minus 1. And here's an example: 100, 105, 110, 115. It's going up at a constant rate, linear trend. And if we difference it, we get 5, 5, 5, right? And you see that there's a constant mean, constant variance, right? And constant correlation, right? It's all consistent. In the real world, we're probably not going to get that, right? So in linear trend differencing, we see a non-stationary series. We difference it. We do get a stationary series, but it looks a little like it could go still, like you might need to difference it, right? But we'll confront that issue a little bit later on when we deal with a quadratic trend. Okay, so but here we do difference it, and it does fluctuate around 0. Okay, so that's the important thing. Now I'm going to be talking about seasonal differencing. It's similar to linear trend differencing, except we're taking a lag of 12, right? So we're taking the original value at t and then subtracting the lag value at 12. So if we look at this example, we see 10, 12, 15, 11, 13, 16. We do y2 minus y1 for January. It's 11 minus 10 is equal to 1. 13 minus 12, 16 minus 15, all equal to 1, right? So we have a constant mean, constant variance, right? And constant correlation. So here's a real world example of seasonal differencing. So we've got a sine wave repeating every 12 months, like a yearly sales cycle with peaks in December, right? And notice how much 12, 24, and 36 Decembers are aligned at the same seasonal high. So there is a seasonal high for that particular part of the year. not the whole year, but that particular part of the year, right? Now, if we difference it, each December value is subtracted from the December 1 year earlier, right? The repeating cycle cancels, leaving flat zeros, no seasonality. Now, it is close to zero, but we will see some type of outlier values, and that is nothing to be concerned about, right? So, I mean, in general, it fluctuates around zero. In real data, you're going to have probably some outlier values that's going to pull the values, in a different direction, but we have differenced it, and it's sufficient. Now I'm going to be talking about different types of trends. We saw a linear trend, and I said that I'd be getting back to what we call a quadratic trend, which is increasing at a far faster rate than a linear trend, right? And this was when you would need a second difference. So we see the original series, which is a quadratic trend. The second graph shows us a first difference, but you can see that it's still trending up. And then there's a second difference. Now it's finally fluctuating around zero, right? It's mean reverting to that long-term equilibrium level of zero that makes modeling possible for the ARIMA. Now we've got another example. Again, we've got the original. We get the first difference. We see that the first difference, it's questionable whether or not, that's sufficient, right? I mean, it's definitely not revolving or fluctuating around zero. So that would be our ticket to say we would need another difference, right? I mean, at first glance, you might be like, is it stationary or is it not? But I think a good rule of thumb is to look at it at zero. And in the second difference, we see that. We see that it is fluctuating around zero, okay? Of course, you've got all these wild values, like outlier values that could kind of throw off our perception in terms of how we observe graphs. But later on, we'll be seeing that with the use of AIC, a maximum likelihood estimation technique, we don't really have to rely on graphs, right? But it's always good to look at these things for intuition as to how things behave. Now I'm going to be talking about the auto regression component. So it says today's value depends on past values, as I mentioned earlier. For this to work, the correlation between YT and YT minus 1 must be stable over time, and I mentioned that as well. And we see that the differencing actually makes it stable around the value of 0. Here in this equation, the autoregressive equation, we see that YT is the value of time series at time t. Phi is the autoregressive coefficient, measures how fast past values influence the present. YT minus 1 is lagged values of yesterday's returns. And ET is today's error term. So here is I'm going to be talking about the moving average component. It says today's value depends on past errors. YT is equal to mu plus error term plus theta 1, ET minus 1 is the general formula. YT is the value of the time series at time t. Mu is the mean of the series. ET is the white noise shock at time t, normally distributed around 0 sigma squared. Theta t is the coefficient that measures the impact of past shocks on the current value. And this makes only sense if the errors are identically distributed over time, IID stationary. And this means that the errors don't have a trend, they don't have seasonality, and always come from the same distribution. Now let's put it together in the ARIMA model, the autoregressive component, the moving average component. Here we see the equation for the ARIMA model, the general form. We see the autoregressive part and the moving average component. And it could be expressed as in shorthand for ARIMA PDQ, right? P, the autoregressive component, D, differencing, and Q, the moving average component. ET could be normally distributed over 0 sigma squared. So how do you choose P and Q? Here we see somewhat of a heuristics guide. We see ARP, the ACF decays slowly. The PACF, it cuts off after lag P. MAQ cuts off after lag Q. And then the PACF decays slowly. So you see that the AR and MA are somewhat opposite. But if we have an ARMA, which is short for autoregressive moving average, right, without the differencing component, it just both decays. Here we see an AR2. You could see that the ACF decays slowly. And then the PACF component cuts off after lag P, which is around 2. So we would get an AR2. For a moving average component, it cuts off, the ACF cuts off after lag Q, which is around 1. And then you could see that the PACF decays slowly, right? And then for this, the ARMA 1-1, both decay slowly, okay? I know there's some room for interpretation in terms of the graphs, and that's pretty common. And again, I'm going to be taking care of this issue with optimizing the AIC, or what we call the Akikai information criterion. So here's the Akikai information criterion. It was invented by a Japanese statistician, hence the term, his last name, I believe, or first name, I forget, is in this formula. So the ARIMA parameters that we're trying to optimize for are phi, theta, and sigma squared. And we could estimate these parameters using maximum likelihood estimation. This finds the parameter values that make the observed data most probable, which is the definition of what maximum likelihood estimation is, okay? And it also assumes residuals are most likely normally distributed. So the maximum likelihood estimation, we see a ARIMA model, PDQ after differencing, right? We saw that formula earlier, that's the ARIMA model. And then we take the likelihood for the residuals, right? If we have all the residuals, ET, the likelihood would just be the joint Gaussian density, where ET depends on the AR and MA parameters. We can make this easier by turning it into the log likelihood, right? And ET is equal to XT minus phi1 XT minus 1, that general formula, plus theta 1 ET minus 1 plus theta Q to ET minus Q. So that's how you derive ET, right? And that's why we're optimizing for phi, theta, and sigma squared, okay? Based on this Gaussian, joint Gaussian density. So I mentioned earlier Akikai information criterion. The exact formula is 2k minus 2 log likelihood of L, right? So we saw the log likelihood. K is the number of parameters, P, Q, and sigma squared. There's only one sigma squared, okay? P and Q, we could change that, right? It could be 1 lag, 2 lag. In our examples, we're always working with 1 lag, but it could be 2 or 3 lags, right? 2 or 3 past values, right? For both the P or Q. And then ln L, natural log of L is the log likelihood, which we just saw. And 2 things you want to do: minimize K, right? Making the model parsimonious, meaning You don't want as many parameters. You want to minimize that because of the fact that the more it makes it messy. Two, simply, using the idea of Occam's razor, making things as simple as possible. That's usually the best bet if you want to interpret coefficients or whatnot, right? Um, so usually one is optimal. Not to say that if there's um, a bigger lag structure or other values that might influence um, your model, that you shouldn't incorporate that as well. We saw that in seasonal differencing, right? It could be a 12-month, it could be 6 months, who knows? But in general, the rule of thumb would be to keep the model as simple as possible. And then you want to maximize the log likelihood, right? The maximizing the MLE, basically, right? Maximum likelihood estimation. And this finds the parameter values that make the most observed data possible, like I mentioned earlier. Now, we saw earlier the ACF and PACF, how we had to kind of visually inspect if it was decaying slowly and where the lags were cutting off. And it runs into some type of, I guess, a perception problem in the sense that you could look at things and then kind of come to different conclusions, and that's possible. But if we do this optimization where we try to minimize the Akikai information criterion, right? We're trying to minimize the number of parameters and then optimize the log likelihood, right? So that we decrease the value of the AIC. We could come up with a P, D, and Q that is our best model, okay? So I'm going to give you the basically the steps here. So we've got our original model that we've mentioned, the ARIMA model, and we could run it on various combinations of 0, 1, and 2, right? And these values could be for the PDQ parameters, right? We could difference it 0 times, we could difference it once, or we could difference it twice. Same thing with P. We could have a 0, no autoregressive component, 1 autoregressive component, or 2. Same with MA. So that's the idea. Obviously, we could create more parameters and run multiple combinations, but let's just, for this example, keep it simple and we just keep it at 0, 1, 2. Now, if we were to create combinations, right, across, we would get about 9 possible combinations, right? The first one being 0, 1, 0. This is just the differencing. And then we've got 0 and 0. And I think the first one, if I recall correctly, is just a random walk. Okay. And then we've got different parameter combinations. So with those parameter combinations, what we could do is for loop on an ARIMA model. So use a for loop on each of those parameter combinations, okay? And then we're going to get a set of outcomes, okay? 9 outcomes to be exact. And we see that this combination of PDQ being 1, 1, 1 has the lowest AIC, right? So that would lead us to an ARIMA 1, 1, 1 model. And then selecting the ARIMA model with the lowest AIC balances fit and complexity, right? Which generally results in the best out of sample forecasts, right? Lower AIC penalizes unnecessary parameters, the K, and it avoids overfitting, okay? So we want to, as I was saying earlier, minimize the K and then optimizes the likelihood, right? It basically, AIC is it penalizes model complexity. And the reason being because we don't want to overfit, meaning we don't want it to be so precise that it doesn't generalize well into other data sets. So that's going to be the end of this video. Thank you very much, and hope to see you soon.